Hello, my name is Isabela Dalmolin Battistella, and I will present the work Analysis and Simulation of Chemical Processes using Machine Learning Algorithms combined with Macroscopic Simulation, developed at the Laboratory of Materials and Scientific Computing at Universidade Federal de Santa Catarina, Brazil, under the guidance of the professors Natan Padoin, Cintia Soares, and Nicolas Spogis. A challenge faced by the industry is obtaining anhydrous ethanol at the purity level specified by the National Agency of Oil and Gas, which is a minimum ethanol mass content of 99.3%. The reason for this is that the mixture of ethanol and water forms an azeotrope with a concentration lower than the National Agency specification. Thus, conventional distillation is not able to promote proper separation of this mixture, and extractive distillation stands out as a viable alternative. However, strict control of the process is necessary in order to avoid input parameters fluctuations from affecting the required purity for anhydrous ethanol. Aligned with the expectations of both research and industry, this work aims to implement machine learning algorithms combined with macroscopic simulation of the extractive distillation process of an azeotropic mixture of ethanol and water. The objective is to infer the product's ethanol content through measurements of the process input parameters. First, the simulation of the extractive distillation process was developed using the chemical process simulator DWSIM. The flowchart of a standard extractive distillation process features two distillation columns. The solvent, in this case ethylene glycol, and the azeotrope are fed into column 1, referred to as the extractive column. This column has anhydrous ethanol as the overhead product and a mixture of water and solvent as the bottom product. This mixture is fed into column 2, where conventional distillation allows solvent recovery as the bottom product, while water is recovered as the overhead product. The solvent obtained is mixed with makeup stream and recycled to the first column. Through the integration of the DWSIM process flowchart and Python tree, it was possible to create a database containing process input and output parameters. To build the database, disturbances were applied to the following input parameters: molar fraction of each component, temperature, and molar flow rate of the azeotrope, as well as the reflux ratio of the first column. With each combination of input values were also stored the process responses, including molar fraction in the product and the overhead flow rate of the first column, as well as the reboiler duty. These input and output data were saved in a Microsoft Excel spreadsheet totaling 5,000 records. With the database ready, 9 regression models were trained, validated, and tested using the Python programming language through Jupyter Notebook. The chosen performance metric was the root mean squared error, or RMSE. It is worth noting that the lower the value for the RMSE, the better the performance of the model over the dataset. This table shows the training and testing errors for each of the considered models. From it is possible to state that the models with the best performance on the dataset considered were support vector machines, random forest, extremely randomized trees, and light GBM regressor. This figure displays the learning curves for the 4 models that best represent the data trends. The blue line represents the training error, while the red line represents the testing error. In this figure, the learning curve for the light GBM regressor exhibits a different pattern compared to the one observed in the other methods. Here, we examine in detail the trend for the light GBM regressor, with the y-axis on a different scale. As can be observed, the training error reaches a plateau at a low value, which indicates a low bias for the model. However, the distance between the curves as they approach constant values indicates high variance. The combination of low bias and high variance indicates that the light GBM regressor method exhibits overfitting. Returning to the previous figure, it becomes clear that the other methods show low bias combined with low variance, conditions that characterize the desired behavior for a machine learning model. Among these algorithms, support vector machines achieved the best performance by showing training and testing error values that are closer, which indicates greater reliability in its predictions. Thus, the use of regression through the support vector machines model proved to be the most promising method in inferring the values of ethanol molar fraction in the product of a extractive distillation of the azeotropic mixture of ethanol and water using ethylene glycol as the solvent. Thank you for your attention.